Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series. And so right now I'm working on some conceptual problems, and these are mostly reasoning stuff. But yeah, okay, let's just hop right into it. So in each of the following cases, either find an example that contradicts the given statement, which shows that it's false, or we explain why this statement is true. Right, so first it's asking, say we have a set of vectors u sub 1 to 3, and we say it's a spanning set for R sub n, then u sub 1 to 4 is also a spanning set for R sub n. So what are we saying here? For letter A, we're saying that the span of u sub 1 to 2 to 3 is actually the same span when we add that fourth vector, and they're both in R, right? And now we're asking what are all possible values for n for which the three vectors can span Rn. It's mostly a reasoning thing, right? So let's think about it for a bit. Okay, I'm gonna be honest, I'm also thinking about it. This is a bit tricky, just a bit tricky. But we think that they both have the same span in Rn. They were saying, well, okay, maybe R3 and S3. That could be possible for the sole reason that if u sub 1 to 3 are linearly independent, then we know we have a three-dimensional space, right? Okay. Where can I'm trying to find a way to like share it, and that's weird. Oh, I could put it vertically or I don't know how layout, I think. Content only. It's fine. I'm just trying to adjust the zoom. Anyway, okay. So, right. So we say that the span of a set of vectors is the set of all linear combinations of those vectors, right? If we add a new vector, it does not remove any linear combinations. In fact, it only adds possible combinations, right? Okay, see? So, it's asking what are all possible values of n. So here I would say n could be less than or equal to 3, right? N could be 3 if we have three linearly independent vectors. N could be 2 if, let's say, two of them are linearly independent and they span R2. And N could be 3 if they're all linear. Wait, it could be 1, right? Okay, let's just see how this works. Right. N could be 1 in the sense that they're just all in a line. N is 2, they're in a plane, N is 3, they're in space. Okay, let's just write that out. So, let's see. U sub spanning set is also spanning set. Okay, actually, the funny thing is the first statement is kind of, it's just a fact. It's not, I don't think it's that helpful. Okay, I'm just gonna write that. So the dimension, what's this? Can't erase. So we're saying that the dimension of the span of these three vectors, u sub 1 to 3, right, is actually 3. The reason is, well, it's really simple. We cannot have more than 3 linearly independent vectors, right? Because if we have more than 3, then that's impossible, since then n would be greater than 3, but given that we only have 3 vectors, we can't really produce an n-dimensional span, right? Say if we have 4 vectors. We have 4 vectors, well, it's not gonna work. In the sense that they cannot span Rn. Yeah. Okay. More than 3. Yeah. Among the 3 vectors. Right. So, or therefore, yeah, it's more like a logical reasoning thing here. Therefore, 3 vectors can span Rn only if n is less than or equal to 3, right? I was thinking maybe we should give an example for each. Does it say to do that? Oh, it says either find an example that contradicts or we explain why it's true. So that doesn't mean you have to find an example if it's true. Right. So we could say, well, n equals 1 is possible because actually, let's just explain it. So we say n equals 1 is possible for the reason that, or since non-zero scalars, or I wouldn't really call it scalars. It's just like, or actually, we can call it scalars. U sub 1 is written as 1, U sub 2 is 2, U sub 3 is 3, scalars, right? We could also write them like this: 1, 0, 0, 2, 0, 0, 3, 0, 0. They could also be written as vectors, but they're just all in the same line, right? Viewed, since non-zero scalars, yes, so they're basically viewed as vectors in R1, right? But who I just stated. So we're just gonna say it's possible. We're gonna do this, like put parenthesis around it. We say they span R1, right? Like the example I gave. Okay, let's do 2. So when it's 2, or when n is 2, it's actually also possible, right? So we can give an easy example here where we say, okay, we have this vector here, this vector, this vector. We have 3 vectors here, and 2 of them are linearly independent, right? Because they only have a trivial solution that goes with them, and that's these 2, right? And actually, this is a linear combination of these 2. If you add those 2 vectors together, you get the third vector. So this one's independent. These 2 are independent, right? Okay, let's see. Let's see a way we could check it is just to solve for it directly. Um, okay. Actually, I shouldn't have done this. This is weird. Or should I have given an example? No, it just tells me to explain. Yeah, actually, I shouldn't have done this. My bad. My bad. My bad. Actually, I could do it. Fine. And then n equals 3, of course, is the obvious reason. Okay, maybe we can just write out for, say, any n greater than 3. Well, it is impossible, right? Since R of n has dimension n being greater than 3, and the 3 vectors cannot produce an n-dimensional span, right? Okay. Now you might be wondering, how about n equals 0? What is that? Well, that's just a single element, which is a zero. Well, no, it doesn't have anything. It's a zero-dimensional vector space, so it's only the zero vector. What's it saying? Possible values of n for which. Yeah, I think n equals 0 is gonna work, but it's kind of abstract. Yeah, so we would have an empty thing, which would be something like u sub 1 is an empty, u sub 2 is an empty, u sub 3 is an empty. And these things would span R0, but it's very trivial, right? So we can only put the zero vector. Okay, it's actually, oh no, that's fine. Yeah, I don't need to write them out. I just need to explain why. Okay, for letter B, yeah, long way to go. If u sub 1, 2, 3, define example, explain why. Oh, should I have explained this first one? U sub 1, 2, 3 is a spanning set, and 4 is also a spanning set. The set with u sub 4 is also a spanning set for the same Rn. Oh shoot, should I have explained that? Uh-oh. I probably should have explained that. Okay, I'll just explain it just to be super, super sure. I feel like writing a paragraph here. Yeah. It's not mostly math that they're looking for in linear algebra, or at least in this class. They're mostly looking for how you can reason with things. I think that's what they're looking for. Oh shoot. But it's so far away. It's fine. Right, so I just need to explain why this is true. So we're gonna say that the span of the set of vectors is the set of all linear combinations of those vectors, right? That's what it means to be in the span. So if, say, this set U sub 1, U sub 2, U sub 3 spans Rn, then we say every vector V, could be W, doesn't matter, which is going to belong to that same Rn, and it can be written as a linear combination of the three vectors that we already have in the set. So it can be written as V equals, say, yeah, we just do this. A sub 1, U sub 1, A2, U2, A3, U3, where we say that A sub 1, A sub 2, A sub 3 are scalars, right? Now, here's the claim it was making, that when we add another vector to the span U sub 4, it actually only adds to possible linear combinations, right? I could say, okay, this is the same, but then I could say U sub 4 is a zero vector, and that would still be the same, right? Or it could be something different, who knows? But it would only add to the number of possible linear combinations. And so we say every V is still a linear combination of the enlarged set. So that's the reasoning behind it. It's really just going all around. Therefore, U sub 4, or no, not U sub 4, V is still a linear combination of the enlarged set, right? And by that, the set of U sub 1, U sub 2, U sub 3, U sub 4 actually also spans Rn. So we're just mixing definitions around, right? That's the explanation for that. Now I want to move this. It's fine. We got space. Right, that's A. Let's go to B. It's more of an explanation type of thing. Showing it's false. Is there something here that shows it's false? Oh, we should give an example for any n greater than 3. Let's do that. Yeah. What if n is greater than 3? Where will it get messed up? Yeah, let's just give a simple example. So let's say n is 4, right? When n is 4, oh shoot, what's happening? The thing is not working. When n is 4, r sub 4, right? And so we say u sub 1 is something that has 4 components, right? U sub 2, 4 components. Here I'm just doing standard basis, right? But here we only have 3 vectors because that's all we're given, right? Now we know these 3 are linearly independent because they only have the trivial solution where the scalars are all equal to 0, right? So we know these vectors are linearly independent. Also because we know they're the standard basis vectors or standard coordinate vectors. And since they're linearly independent, so span is something. U sub 1, U sub 2, U sub 3, right? You could say it's this vector here, x, y, z, 0, such that x, y, z are basically numbers or scalars, right? Right. Okay. So here, this is actually a three-dimensional subspace inside R4, and it does not include vectors like 0, 0, 0, 1. Okay, I'm just gonna write that one out. But yeah, the idea is we have 3 linearly independent vectors. So it's actually impossible if we have if the number of dimensions is greater than the number of our linearly independent vectors. It's impossible for the 3 vectors to produce an n-dimensional span. So here in this case, when n is 4, right, we have 3 vectors. So we're saying this is actually a 3-dimensional subspace in R4, right? So it doesn't include vectors such as, well, I'll keep it simple, 0, 0, 0, 1. So the span of these things, or of our 3 vectors, is not R4, right? So that's what it's saying. Okay, good. Now I did A. Okay, let's do one more, and then I'm gonna take a break for a bit. If U sub 1, U sub 2, U sub 3 is a spanning set for Rn. So we're saying the span of those is Rn. Then U sub 1 plus U sub 2, U sub 1 minus U sub 3 also spans Rn. Man, this is some proving crazy. Let's see. Yeah, let's think about it for a bit. So we want to find an example that contradicts the statement showing that it's false. Is this false or is this true? That's the first thing we want to know. Linear combination. I could write it out that way. U sub 1 plus U sub 2 is actually a linear combination. U sub 1 minus U sub 3 is also a linear combination. So from there, I would say it is always true. Right? If they're linear combinations of each other. So, okay. So we suppose U sub 1, U sub 2, U sub 3, the spans Rn, right? And now we want to consider the set. Let's do S. The set is that U sub 1, U sub 1 plus 2. Or no, what am I saying? U sub 1 plus U sub 2. Oops. And then U sub 1 minus U sub 3. And that should give me something, right? So we want to show U sub 1, U sub 2, and U sub 3 lie in the span of S. Right? Okay. See, think about the way to write it. Okay. So to show that, well, we can see U sub 2 here is actually U sub 1 plus U sub 2 from the set S minus U sub 1. And so we say, well, it is. Does belong in the span of S. Let's look at U sub 1. No, U sub 3. Oops. So U sub 3. So here actually, we're looking at a linear combination of these guys. right? U sub 2 is a linear combination of those two vectors, or here technically we see three, but it is a linear combination, so we say it's part of the span of F, right? That was our previous definition. Now, U sub 3, we can say that's just, what is that? Well, that's actually U sub 1 minus U sub 1 minus U sub 3. So again, with this linear combination, so again, it's also in the span of S. And then we have these two. U sub 1's already in the span. Right? There. It's literally there. So we're saying the span of this is actually the same as this. Because we can write a linear combination of these vectors in set S. Make vectors, or to make linear combinations which are vectors of these guys. Hope that makes sense. I'm yapping too much. Okay. Right. So what else am I saying? An example contradicts. No, it's always true. Yeah, I did. So therefore, we can say that span of E sub 1, E sub 2, E sub 3 Okay, I can't really write notation. Okay, the spans Rn and span of this guy. I forgot what it was. Sub 1 plus E sub 2. E sub 1 minus E sub 3 is also Rn. It's really as simple as that. Not too complicated. They both span Rn. Okay, can I finish this or that's fine. I'll go through it later. Yeah. Okay. So that's it for this video. I hope you guys enjoyed, learned a lot. I still got a couple more exercises to go for, but I hope you guys enjoyed, and I'll see you all in the next one.